Lesson 8.6, simple compound and continuously compounded interest. Right, so just like 8.5, I don't think there's anything extraordinarily new, but it is nice to have these last couple lessons, 8.5 and 8.6, just to have more practice with logarithms and exponents. Right? And so here's again a refresher of some log rules. Okay, so if you have x to the y z, you can rewrite that in terms of logarithms. Log base x of z is equal to y. You got that. Here's this product property. You can add logarithms. There's this quotient property. You can subtract logarithms. Log of a to the b is b times log of the a. You take that power down. If you want to change base, if you have some weird base, log base b of a, you can write that as log b, or sorry, log a over log b, or natural log a over natural log b, as long as the basis of the new logarithms batch. Okay? And I got a couple of bonus facts down here. All right, so there's some log rules. All right, your book showing you on lesson 8.6, we have simple interest, compound interest. If those are really small, I'm going to write this bigger for the camera. Okay, so we got simple interest, compound interest, and then continuously compounded interest. Okay, so we got A equals P and 1 plus the interest rate to the power of time. If you compound to some number of times during the year, you got the amount is equal to the principal times 1 plus the interest rate divided by the number of divisions to the power of nt. Right? So if it was compounded monthly, n could be 12, and that would show up two places in the equation. Okay? Then your continuously compounded interest, A equals P e to the power RT. Okay? Now this one is really different class looking curve because interestingly, the interest rate is showing up in the exponent. Right, that wasn't true for simple or compound, but continuously the interest rate does show up in the exponent. Okay. Okay. And also, I showed you guys, if you look back at the previous lesson, there's kind of a translation from one to the other. Right? So if you know continually compound interest rate, you can find a simple equivalent or vice versa. Right, so what are we doing here? Example 1, use simple interest. Jeremiah invests $3,500 into an account with 7% annual simple interest rate, making no other deposits or withdrawals. What will be his account balance after 6 months, a year? Okay, so example 1. Let's use the amount is equal to the principal times 1 plus the interest rate, right, time. Okay, so he puts in $3,500. You're gonna say, how much does he have? So very simple. Okay, just plug it in and times. Now his interest rate is 7%. Okay, so 7% as a decimal is 0.07. Put it all together, add one. That's 1.07. And then to the power of however much time has passed. Okay. So like if 1 year has passed, that's one thing we're going to solve. Okay. Then the amount that he's put in is grown by 7% because it's times 1.07. You guys see how that works. Okay. So let's start with 6 months. So the amount after 6 months is, see, 3,500 times 1.07 to the power of. Now, guys, do I want to put 6 up here? No, because that would represent 6 years. I'm looking for 6 months. Okay, so I need to convert months to years. I can either write 6 over 12, as in 6 months out of 12 months in a year, or 0.5. It's like, oh, well, I know 6 months is half of a year. You could totally put 0.5, it's the same thing. Let's try this. So it's 3,500 times 1.07 to the power of 0.5. Okay, I'm looking at $3,620.43. Well, I should put a dollar sign right here. I mean, that is the unit we're working with. Okay. So this is after 6 months. Okay. Also, your back asked, what I have after 1 year? Okay, so let's treat this puzzle B, I guess. The amount after 1 year. Okay. So there was still the original $3,500. But now, okay, also 7% interest, but now we're letting this go in for 1 year. So power one. Yeah. So 3,500 times 1.7. This would be dollars, $3,745.00. All right, let's see if that's what your book got. They should give me answers on this. Let's see. Um, what was account balance? Am I not? Oh, okay. They left some blanks here. I mean, that's what it would be, though. All right. All right. That looks about right. Right. It looks reasonable. All right. Example 2, compound interest. Over here. Leilani invests $2,000 in an account of 5% interest compounded quarterly. That quarterly. Example two. Right, no other deposits or withdrawals. So she's just gonna throw in some money and just leave it there. What's her account balance after some amount of time? Okay, so let's take A equals P times, right now this one was a little different. 1 plus interest rate over N to the power NT. So the amount she'll have, let's see, she put in $2,000. That's like a principal right there. Times 1 plus, the interest rate is 5%. Remember, as a decimal, it's called 0.05. That's like the calculator understanding of 5%. But it says compounded quarter. Okay, so where n goes, I'll put 4. And then to the power of 4, and then t. Okay. So here's a good general equation. It'll say the amount as a function of time, something like that. Okay. Then after 6 months, well, 6 months is 6 over 12 or 0.5 years equals, well, I'm just going to plug in 0.5 here for t. Okay, you guys saw that in the last example. Okay? That 6 months is the same thing as half of a year. You guys get that? Okay, so 1 plus 0.05 on 4 to the power of, and then in parentheses, oh guys, yeah, when we put this calculator, make sure that this power is definitely in parentheses. Otherwise, what the calculator is, so put to the power of 4, and then it'll turn around, multiply by time, and it'll give you a nonsensical answer. So we gotta have a parenthesis here. And then 4 times, and then half a year, right? Because it's sort of like, okay, like if you divide this interest rate by 4, it's really a much smaller interest rate. It's like 1.25% interest, right? But it is every quarter of a year, right? So it's like multiple times you're compounding it. Right? I mean, it's good to think like why this formula would take this structure, right? And I mean, I can sit here and explain it. I kind of just did, but really the only way to understand it is like sit down and think deeply about it. I mean, that's true for so much in math and science, right? Anyway, I got all keyed up in my calculator. So looking at 2,000, whoops, and $50, 2050, and 31 cents. There you go. Okay. That's at 6 months. Okay. If I go back and where the t was, instead of half a year, let's do 1 year. Try that. So the amount after 1 year, so it's like a function here, is $2,101.89. So this is at 1 year. Yeah, I mean, I think that looks about right? Yeah. So after 6 months, she's picked up an extra $50 worth in interest. And after another 6 months, yeah, a tiny bit more than that. The original 50 is like 50 plus another 50. Plus, the $50 she accumulated is also accumulating its own interest. It's following an exponential curve. Okay. All right, so we did a simple interest. We did a compound interest. Okay, now let's do continuously compounded interest. Now, G, who borrows $1,800 at 4.5% interest? Example 3. Right, well, it's continuously compounded. Now we're using that A equals P e to the RT. It does not make any withdrawals or payments. So sorry, what am I saying withdrawal? Sorry, he's borrowing, right? You guys, this is the flip side of interest, right? Like these other ones we're looking at, like, oh, okay, we're depositing into an account that's accumulating interest on the depositor's behalf, right? But this guy is borrowing, he's taking out a loan. He's gonna have to pay this back, right? He would preferably like a smaller interest rate, wouldn't he? Right? So the amount he owes is, right, let's take the original withdrawal, the amount he borrowed, which was $1,800. Okay. And we'll say times e to the power of, okay, now this R interest rate, it said 4.5%, but the calculator value is 0.045 is a decimal. How much will you owe after 6 months in a year? Okay, 6 months a year. Okay. So here's your general formula. I'll say A is a function of t time. Okay. So how much does he owe? How much does he owe the bank? So let's say after 6 months, which would be half of a year. Right. So I'm going to plug in 1,800 times e to the power of 0.045 times 0.5. He owes $1,840.96. This is at 6 months. Okay. Then after 1 year, suppose he's like, okay, I'm just gonna not pay anything back yet. So he's going to check at the end of the year and see how much does he owe. And for that, where the 0.5 years was, I'm just going to put 1 year. I'm looking at 1882.85. All right, there you go. All right, good. Boom. All right. So go. Okay, example 4. Compare types of interest. Tom wants to invest $1,800 at a bank. Oh, interesting. Same amount. Okay. At a bank that offers 3 different accounts. Account A earns 8% annual simple interest. Account B, 8% interest compounded annually. That's the same thing. Maybe they wanted you to catch that. Right? Account C earns 8% compounded continuously. If no other deposits or withdrawals are made, compare the balances after each number of years. Let's just say 1 year. Okay. Yeah. Okay. That's kind of what we just did, isn't it? All right. Actually, here's what I'm gonna do for this one, because we basically just did all of these. Right? I'm just gonna hold this close to the camera to point out what they did. Right, so here's your simple interest. P1 plus, wait, that's a typo. That's a typo. Never mind. Sorry, I'm just gonna write this out on paper. Right, so account A got simple interest. We got the amount is equal to the principal times 1 plus the interest rate to the power of t. Yeah, this shouldn't be RT. This should be 1 plus R closed parenthesis and then to the power of t. That's what it should be. Okay. So the amount would be $1,800 times 1 plus, okay, 8%. That's 0.08. So collectively, this is like 1.08 if you like. Okay. And we're going to let this go after 1 year. So 1 year. Okay. So what's 1,800 times 1.08? Okay, that is $1,944. Part B, I say compounded annually. Right? But that's got to be the same thing. Simple interest and compounded annually. There's no difference between the two. Okay? So this is A equals P1 plus, and then R over 1 to the 1t. But you guys see that these are the same. So the answer is the same. $1,944. It's no different. Okay. Now, how about continually compounded? Right. This one should give us a larger value. Right? Continuous compounding. Right. So A equals P, which is 1,800, times e to the power of 0.08 times t, and t is 1 year. Right, so I'll just run that. So what is 1,800 e to the power of 0.08? Okay. Okay, no, it should be larger than 1944, but probably not very much larger. Let's see. Yeah, exactly. 1949.92. All right, so bigger, but not by very much. Yeah. Boom, boom, boom. Example 5. Use logarithms to solve equations. Lorenzo invests in an account that earns 3.2% interest compounded semi-annually. Okay, so that would be twice per year. So it's being compounded twice per year. If no other deposits or withdrawals are made, how long will it take for the investment to double? And notice it never told you how much he invested because that's irrelevant to the question uh, to double, right? He could put in $10 and double it to 20 or $100 and double it to 200. It would take the same time at that particular interest rate. Example 5, right? And I'll show you guys. So we're doing the amount is equal to the principal times 1 plus R over, now, yeah, I'll just do N and then NT, right? So the what we're going for is, I want this A to be 2 times the original principal. Okay? So he puts in some principal P, it's going to eventually double. For the interest rate, 3.2%, I'll write that as 0.032 as a decimal. Right? And then semi-annually, N is equal to 2. So compound like twice a year. And the question is, how much time does it take? So we're solving for this t, which is in the exponent, which means we're going to have to use logarithms to solve it exactly what it says. Remember I told you guys, it doesn't matter how much it puts in, $10 or $100, because regardless of the answer to double would be the same. So now I got this. Show you, I'm going to do this. I'm going to do natural log of both sides. Natural log of 2 equals natural log of all this. Okay? And I'll write that down. Natural log 2 equals natural log of, what if I can clean this up? Yeah, I sure can. Because 0.032 over 2 is 0.016, and I can add that to 1, take a look like this, to the power of 2t. This is, we're taking natural log of all this. Okay. Right now, because of we point out the rule I'm about to do, I'm thinking of this one right here. Log of a to the power of b is b times log a. Well, we did that right here. And take this 2t, we're going to in front right here. So that would be natural log of 2 is equal to 2t natural log of 1.016. Right? Then divide both sides by both 2 and natural log 1.016 to natural log 1.016. Okay, let's see. I'll get a value for t. Okay, I'm just going to type in this right here. So this is going to be the answer. So natural log 2 divided by, and then in parentheses, okay, really important you throw some parentheses right here in the calculator. 2 times natural log 1.016. Looking at 21.83 years. Yeah, so between 21 and 22 years. Okay. Does that make sense? Well, 3% interest. Okay, so roughly 3% interest. Okay, yeah, compounded twice a year or whatever. Okay. Yeah, I could see it could take more than 20 years for your investment to double. That looks about right. All right, book puzzles we got here. Number 3. Marquis borrows $900 with 3.8% annual interest rate compounded continuously. He does not make any payments. How much will he owe after 2 months, 18 months? Oh, okay, so let's accrue interest here. All right, so annual interest rate compounding. As soon as they say compounding continuously, you know to use A equals P e to the RT, some version of that. Okay, he's going to borrow $900, so where P goes, I'll put 900. Well, I could call it 8 not. It doesn't matter what I call it though. It's still $900. All right, times e to the interest rate is 3.8%. So where the r goes, I'll put 0.038. And then how much will he owe? Well, here, let's make an equation first. All right, so like a function. So the amount after a function of time, amount in terms of time is that. So we got that expression. Now let's let t be 2 months. Isn't that 2 over 12 years? Isn't what that would be? Okay. So A of 2 months out of 12 months in a year. So 2/12 of a year, you think it that way. So this is a function. Equals, we're going to take the $900 times e to the 0.038 and then times 2 on 12. It's all in parentheses here. Okay. Now, if only 2 months have gone by at this relatively small interest rate, it's probably not going to be much more than 900, but let's see exactly. 900 e to the power of 0.038 times 2 on 12. That's all in parentheses up there. Is, yeah. $905.72. Okay. Okay, so yeah, small interest rate for just a couple of months. Didn't go up very much. Okay. All right, let's try the amount after, what was the other? 18 months. Well, 18 months compared to 12 months. You could also call that 1.5 years if you like. 1.5 years. Okay. 18 over 12 equals 1.5. A little flat file over here. Okay, so that would be, take your $900 times e to the 0.038 times 18 over 12 or 1.5 if you like, throw that all in parentheses up here. Okay. Let's see how much after a year and a half. And so all I have to do is scroll up, scroll over, and where the 2 over 12 used to be, I'll put 18 over 12. Okay, and that's going to be $952.79. Yeah, looks about right. Number 5, investing. Kenneth invested in an account that earned 2.2% interest compounded continuously. You know the deposits withdrawal made. How long will it take your investment to triple? So the amount is equal to the principal times e to the RT. Okay. So what we're going for here is 3 times the principal she put in originally. Okay. Notice it doesn't say how much she put in, but again, that doesn't matter. Put in $10, $100, $1,000. It takes the same time to triple whatever value. In the place of R, okay, the column 2.2%, so we'll put 0.022. Okay. And then we're solving for this t. Solve for t. Take the natural log of both sides. So this is multiply. Sorry, that should be multiply. Okay. But whatever, because the p canceled out. So I'm taking the natural log of this side. Natural log, natural log. So natural log of 3 equals natural log of e to the 0.022t. I could take this power right down in front. So natural log of 3 is equal to 0.022t. The natural log of e, of course, is 1. So change it. Divide those sides by 0.022. 0.022. Okay. So the amount of time it takes the investment to triple is whatever this is right here. Natural log 3, close parenthesis, over 0.022. Looks like, 49.94 years. I mean, you could call it 50 years. Yeah, that looks believable. Like 2.2% interest, that's a fairly small interest rate. Okay, so to triple, yeah, it would take about 50 years. Okay. You know what? If we weren't talking about interest, if we were talking about inflation, it could be the exact same curve, the exact same model. Okay. So if you guys take in, say, an economics class, you probably learned that the Federal Reserve is the central bank, at least in the United States, right? And oftentimes central bankers aim for approximately 2% inflation, right? But they might miss it here and there, right? Let's say they kind of average about 2.2%, over many decades, which could be modeled by this. So we got this, right? What that would mean then is that, so you're watching prices go up, say in the stores, and the value of your dollars, of course, decreasing. So you could ask a similar question, like maybe the same question by symmetry. How much time would it take for the value of your dollar to decrease to a third of its value, right? And that would be about 50 years, right? Or you could say, how far back in time do you have to go for your dollar to be worth triple of what it was? The answer would be 50 years. Okay. So we're in the year 2026. If I subtract 50, it goes to about 1976. Okay, so what that means is whatever you can buy with the dollar today, assuming inflation was about 2.2%, it's a big assumption, right? You could buy it approximately 3 times the stuff in the store you could with the same dollar in 1970s. Okay. All right. Boom. What else we got here? All right, so let's do a couple more with you guys. Number 7. What's this? Consider $100 investment with 15% annual interest. Rounding to the nearest tenth of a year, calculate how long it will take the amount to double if the interest rate is simple, compounded quarterly, or compounded continuously. Okay? So I don't think the answers are going to be radically different from each other, but let's play it out and see. No, $100 doesn't matter specifically. It could be anything because we're gonna we'll want this to double regardless. So I'll call this questions A, B, and C. So let's have here. Should give you guys this. The principal is $100, which doesn't really matter anyway. The interest rate is 15%, which we're gonna actually type 0. Oops, that's not right. 0.15. There you go. That looks better for the interest rate. And we want this to double. Okay? So interest rate is simple. So if it's simple, that's the amount is equal to the principal times 1 plus the interest rate to the power of t. Okay, so we know that. We're going to put $100 here, and we want it to double to $200. 1.15 to the t. We're going to solve for t. All right, let me do that. So divide over $100. I'm getting 2 equals 1.15 to the t. I'll take the natural log of both sides. Then I can first pull the t out in front. So natural log of 2 equals t times natural log of 1.15. Divide both sides by natural log of 1.15. And the amount of time to double with simple interest is whatever this is. Natural log of 2 over natural log of 1.15. Looking at 4.96 years, I'll call it. Let's go to the nearest hundredth. Okay. Again, this was with simple interest. Right. That was the model we set up from the beginning. Right. So here's simple interest. We'll keep that on this page. So we'll call that part A. Now 7B, they want to go with, where was it? Compounded quarterly. Here, it's compounded quarterly. So we'll say the amount is equal to the principal times 1 plus r over n to the nt. Okay. So again, we're aiming for $200, starting with $100. 1 plus 0.15 divided by 4 to the 4t is compounded quarterly. Okay. Right, so similar step of the similar process, this series of algebra steps. Divide by 100, that's the first thing we did anyway last time. So 2 equals 1, let me clean this up. What is 1 plus 0.15 on 4? Just get out of that. 1.0375. All right, let's actually work with to the 4t. Okay. Okay. But you guys know what I'm going to do next. I'm going to take the natural log of both sides, which means I can take this 4t and shuffle that off in front. So natural log 2 is equal to 4t natural log 1.0375. Okay. Divide both sides by both 4 and natural log 1.0375. 4 natural log 1.0375. Okay. As long as you get all the parentheses correct in the calculator, this should be the answer right here. That should be the answer. So t equal, okay, and this is, let me spell this out, compounded quarterly. T equals, so let's take natural log 2, divide by, and then in parentheses, gotta have parentheses here to get this correct. Right? Make sure you're doing that practice. 4 natural log 1.0375. Okay, before I hit enter, let's make a little prediction here. Okay? Is back to the simple interest, I remember it took like a shade less than 5 years. But you know what? If I'm compounding more often than just annually, I bet the number's going to shrink a little bit. And it's going to be, well, smaller than this, but maybe not very much smaller. Let's see. Yeah, okay. 4.71 years. Yeah, it is, right? So we reach the doubling value a little faster, right? So at 4.96 years, now it's 4.71 years, right? I bet if we compound continuously, we'll reach the doubling value even faster than this. Let's try it. Okay, so 7c. Now we're going to use a equals p e to the rt. That's for compounded continuously use that. Okay, so again, we're aiming for $200, starting at $100. So times e to the, and in place of r, I put 0.15, and then we're solving for t. Like that. Divide both sides by $100. So now 2 is equal to e to the 0.15t. Take the natural log of both sides. So natural log of 2, right? And all this simplifies to very simply 0.15t with your log rules. Divide both sides by 0.15, and we'll get the answer. Right, the answer is going to be this right here. Let's see, so time is equal to, what is natural log 2 divided by 0.15? Yeah, it is a little faster. It sure is. Sure is. 4.62 years. Okay. And so let's put them all up here. Yeah. So here's your simple interest. Simple interest takes 4.96 years. Here's compounded quarterly, takes 4.71 years to double. Right? And compounded continuously only takes 4.62 years to double, which is the fastest of these three methods, which makes sense, right? Should. Right, and let's do one last one. I was recording. Number 10. Analyze problems. When is a simple interest investment more advantageous than a compound interest investment? Okay, so how can I put this over here? Okay. Let's call simple interest and compound interest. Okay. Let's see what these would be. Okay. So I'll come up with how about an example number? So for example, simple interest of 10% or 0.10 as a decimal. Okay. What would be the equivalent compound interest rate? Well, if you do e to the power of 0.1, you guys have done this before. It should have was a previous quiz question even. Okay. That's more like okay, 1.10. Let's see if I subtract off 1, okay, and then times 100 to turn that back into a percentage. That's 10.52 almost percent, or so I'll say equals approximately 0.1052, something like that. Okay. So if you were to advertise, like if a bank was to advertise a 10% interest rate, okay, if it's compounded annually, which is also called simple interest, then that would actually be the interest rate, would be 10%. Right? But if it was compounded, continuously, I meant to put compound continuously. Continuously, that's what I meant to right over here. Continuously compounded. Okay. The actual annualized interest rate is about 10.5%. Okay. So I think the advantage of each one depends on, are you making an investment or are you taking out a loan? Which side of the equation are you on? If it's simple interest, this would be the advantage to the bank. Right? Let's say maybe offering like paying paying interest on deposits. The advantage of bank paying interest on deposits. Okay. Because the number is smaller, so they don't have to pay as much. Okay. Over here, if it's continuously compounded interest, this would be advantage to the depositor earning interest on deposit. Right. But what about in case of loan? Because those are both examples for deposits. Right? What about if you took out a loan? Now, if you took out a loan, suppose the bank advertises, oh, 10% interest on this loan, but really they're compounding it continuously behind the scenes. Well, now that would be to their advantage, to the bank's advantage, to to compound more often. Right? So now this would be advantage to the bank uh, on a loan. Right? And you, on the other hand, like if you were just a person who was taking out a loan, you would rather have a smaller interest rate. So over here, simple interest would be advantage to the debtor on a loan that they took out. Yeah, right. So, right, right. So the bank would want to uh, give simple interest on deposits to their depositors, right? But the bank wants to compound continuously to the loans that they offer. Right? So maybe they advertise this, but they actually, yeah, like compound continuously. Okay? Right? Maybe they advertise a smaller rate, but the effective rate annualized is larger because it continues compounding. Right? On the flip side, if you're just a person who's just interacting with the bank and you're either making a deposit or you're taking out a loan, right? Well, now the advantage is flipped the other way. Right? So you would rather your own deposit be compounded continuously because that's a slightly higher interest rate. Okay? But if you took out a loan, ooh, now it would be in your advantage to actually have the smaller advertised rate, which would be a minus on interest. All right, so there you go. And that is a wrap on the entire module 8. Here, close out with the log rules again. Here you go. There's all the log rules we've been using for all of module 8.